Okay, so this is a real short video on just the alkyne synthesis using essentially two E2 elimination reactions. Okay, so we will have two dehydrohalogenation reactions occurring. And we have two different types of dihalides here. We have a vicinal as well as a geminal. So the vicinal is when we have two halogens on two neighboring carbons. And this is where the name vicinal comes from. Okay, so I like to personally relate it to the Spanish word for neighbor, vecino, or vecina. I'm sure there's other ways you can relate it to to basically help you remember what vicinal dihalides means. And then there's also geminal dihalides. That's when we have two X's or two halogens on the same carbon. Okay, so for this one, geminal is basically coming from the word geminus, meaning twin, like Gemini, right? So I'm not sure if you guys are into horoscopes, but Gemini's sign is basically twins, and so that's pretty much it in terms of identifying or kind of classifying the two different types of dihalides, and these are both necessary to form the alkyne in two subsequent dehydrohalogenation reactions. And it requires an uber strong base. So usually you're going to see an amide, or sometimes you might see a terbutoxide with DMSO as a solvent. So a polar aprotic solvent that's not going to solvate the negatively charged terbutoxide, and so it's going to make it a stronger nucleophile, strong enough to actually remove two protons from this vicinal dihalide. So it is step by step, don't get me wrong, but I mean overall the net process of removing two. Okay, and we're going to need two equivalents of each of these bases. We might see the amide next to a sodium cation or a potassium or lithium cation. Same for the terbutoxide. So don't get confused when you see like NaNH2. And then also don't confuse NH2 with NH3. Okay, so this is really important because we will see more of the sodium amide in later reactions, and we will also see ammonia too, which is NH3. All right, so check this guy out. We have those chlorides, they're twinning. You know what I mean? So they're on that same carbon. They're geminal. This is a geminal dihalide. And so those hydrogens are also said to be geminal, which is important for the discussion in terms of like NMR, right? So diastereotopic protons, for example, that are geminal. But we have sodium amide, and we have in parentheses above that reaction arrow two equivalents. Okay, so this is important because it's kind of telling us like, hey, we need two of these things to do something, right? And so if you forget the reaction, well, it's a strong base, so why not rip off a proton? Okay, we rip off that first proton, we're going to form an alkene. Okay, and so I'm going to actually bring it on down instead of straight across because I want the product to be on that right side of that arrow. So once we form the alkene, remember the most stable alkene, especially for like if we have large groups like a benzene ring, is going to be that trans alkene. So we're going to have a hydrogen on the upper left and then a chloride on the lower right. Okay. Now, that second equivalent of sodium amide is going to want to come along and rip off that blue hydrogen. And that's why we need such a strong base, because that carbon-hydrogen bond right there is between a CsP2 carbon and a hydrogen. So that's a stronger bond than the original hydrogen, which was a CsP3 carbon bound to a hydrogen. Okay, so once we do that, we end up with this linear alkyne with the two benzene rings on either side. Okay, so that's pretty much it. You know, this step or this particular type of synthesis is Not difficult as long as we understand the general requirements. Super strong base like sodium amide or terbutoxide, and then we need a vicinal halide, vicinal dihalide, or a geminal dihalide. Okay, and again, two subsequent dehydrohalogenations. So to learn the terminology, because you could see it in the question, right? So, or just when I say it, so that way you have a better understanding. This particular step, again, that's the one that's requiring that super strong base. And I probably sound like a broken record because I'm repeating myself, but hey, it's important. So don't forget about the CsP2 hydrogen bond that's stronger than the CsP3CH. So write it down, take a picture, just remember it, okay? And that's it. So have fun with it, get some practice in, okay? Bye.